Prime movers, diesel engines. Objectives: recognize the purpose of diesel engines. Understand the principal operations. Introduction to the different types of engines. Understand how diesel engines work. Troubleshoot diesel engine common faults. Appreciate advantages of diesel engines. Evaluate the requirements for pre-startup and routine monitoring checks. Look at diesel engine safety considerations. Recognize the prime mover selection comparisons. Introduction. Diesel engines have a multitude of applications in the petrochemical industry, typically used as backup power generator and fire water pump drivers, in the static form, and every application from trucks and buses to welding plants in its portable form. The high energy density and relative safe nature of the fuel, with the robust design and construction required to manage high compression, makes the diesel engine a very efficient, safe, and reliable driver option. Diesel fuel is a heavy component found in crude oil, and is used in diesel engines. When crude oil is heated, different substances are separated out and diesel is one of them. Refining crude oil separates diesel as shown in the distillation column diagram around 300 degrees Celsius. The diesel engine is an internal combustion engine that uses the heat of compression to initiate ignition to burn the fuel that has been injected into the combustion chamber. Spark ignition engines, such as a petrol engine, gasoline engine, or gas engine in contrast to the diesel engine, uses a spark plug to ignite an air-fuel mixture. Diesel engines are more fuel efficient compared to petroleum engines. Diesel versus petrol analogy: diesel is 33% more efficient than gasoline engines. More rugged engines than gasoline. Greater torque allows for greater power. Does not explode, however it will burn. Applications: industrial power plants, ships and offshore facilities, trucks, buses and cars, heavy mining equipment. Basic cycles introductions. All engines have 4 stages of operation: the intake, compression, ignition, power, and exhaust. 4-stroke engines take 2 cycles of the piston to complete the 4 stages. The piston travels up and down the cylinder twice per cycle. 2-stroke engines complete all 4 stages in 1 cycle. The piston travels up and down the cylinder once per cycle. PV diagram for the ideal diesel cycle. The cycle follows the numbers 1 to 4 in clockwise direction. In the diesel cycle, the combustion occurs at almost constant pressure, and the exhaust occurs at constant volume. On this diagram, the work that is generated for each cycle corresponds to the area within the loop. The 4-stroke petrol engine is fundamentally the same as the diesel engine, with a spark ignition. 4-stroke diesel engines, the most common type of diesel engine, which is used in all applications. Intake: the air intake valve opens and allows air to be drawn by the retracting piston into the cylinder. Compression: the air intake valve closes, and the piston strokes up the cylinder, compressing the air to a very high pressure, which in turn heats the air to a very high temperature. Ignition: power: diesel fuel is injected into the hot, compressed air which auto-ignites. Ignited fuel rapidly expands, and the enormous pressure drives the piston down inside the cylinder. This is called the working stroke. Exhaust: the piston having completed its downward work stroke, returns up the cylinder. The exhaust valve opens, and allows the burnt fuel, exhaust gases, to be pushed out of the cylinder. Then the 4-stroke cycle begins again with the intake. Diesel engines typically have cylinders in pairs with 4, 8, or 12 being most common, although balancing the drive shaft is the primary determining factor. Single cylinders are used for small applications. 2-stroke engines: the photo is that of a radial 2-stroke diesel engine. 2-stroke diesel engines are typically extremely large, and found in locomotives, large ships, and generating facilities, very similar to the 2-stroke gasoline engine. A 2-stroke reciprocating engine cycles the piston in 2 strokes, completing the conversion of chemical energy, fuel, into mechanical energy, work. Compression: the piston moves up the cylinder, compressing the air charge as the crankshaft rotates clockwise. Air is introduced inside the cylinder, and compressed as the piston is mechanically pushed up by the crankshaft rotation. By the time the piston is approaching the top of the cylinder, known as top dead center or TDC, The pressure is over 100 bar with a temperature over 500 degrees Celsius. Just before TDC fuel is injected into the cylinder by the fuel injector, the fuel is atomized into tiny droplets, a mist. Ignition, power. Because they are very small, these droplets heat up very quickly, and start to burn as the piston passes over TDC. The expanding gas from the fuel burning in the oxygen forces the piston down the cylinder, turning the crankshaft. Burning fuel releases useful energy, expanding gas, as the piston moves down the cylinder. Exhaust. At about 110 degrees after TDC, the exhaust valve opens, and the hot exhaust gas begin to leave the cylinder. Hot exhaust gases consist of nitrogen, carbon dioxide, water vapor, and unused oxygen. At about 140 degrees after TDC, the piston uncovers a set of ports known as scavenge ports. Ignition. The exhaust valve then closes, and compression begins once again. Root air blower. The blower pushes the exhaust gases out, and recharges with air for the compression stroke. Forced air requirements reduces the application of the two-stroke engine to small equipment. Advantages of diesel engines. Key advantages of using a diesel engine: reliable backup power generation, portable, easy to operate, high torque, efficient, and robust construction. Gasoline engines convert 30% of their fuel energy into power, diesels convert 45%. Diesels are more reliable, they don't need high voltage ignition systems. Diesels last longer because parts are stronger, and the fuel has superior lubricating properties. Diesel engines tend to last twice as long as gasoline-powered ones. Diesel fuel is safer. Diesel fuel doesn't release fumes like gasoline does, it's more difficult to burn, and won't explode like its lighter counterpart. Diesels are more easily turbocharged. Diesels produce minimal carbon monoxide. Gasoline engine exhaust can be deadly in confined spaces. Diesel engines can easily accept synthetic and variations of specification fuels. Prime mover comparisons: electric, steam, and diesel. There is no best option for all applications, and each prime mover has its advantages and disadvantages. Electrical driver positives. Electrical drivers are more efficient depending on power source. Cheap, low operational costs and reliable. Easy operation and maintenance. Various sizes, ranges and applications. No direct emissions. Electrical driver negatives, dependent on an electrical source. Vulnerable to power grid failures. Require fixed power source. Cabling requirement. Not suitable for remote locations. Steam driver positives, usually cheap, and available power source. Integrates into the process. Minimal electrical supply requirements. Efficiency dependent on steam source. No direct emissions. Steam driver negatives. Steam efficiency can be the lowest form, depending on steam source, as an example, if produced as a waste stream from a production unit. Requires a fixed piped steam supply and condensate system. Steam source dependent. Vulnerable to steam supply failures. High cost and maintenance. Diesel driver positives, good efficiency. Independence from fixed energy sources. Flexible. Reliable. Easy operation. Various sizes, ranges and applications. Diesel driver negatives, high cost and maintenance. Toxic emissions and flammable fuel. Often very noisy. High operational costs, in relation to other drivers' best available efficiencies. Comparison is impossible without a specific scope of requirements for each driver. Each type of driver serves a unique purpose, and all major facilities generally use a mix of them all. Diesel is the primary emergency backup option. Now let's look at operational principles pertaining to diesel engine fundamentals. Diesel engine principles. The diesel engine is an internal combustion engine designed to convert chemical energy available from fuel into mechanical energy. Pistons are connected to a crankshaft, and the up and down motion of the pistons, known as linear motion, creates the rotary motion needed to turn and drive a device. Diesel engines convert fuel into energy through a series of small explosions or combustions. Air is compressed first, and then the fuel is injected. Because air heats up when it's compressed, the fuel ignites. This massive pressure increase and drives the piston. Principles of the four-stroke cycle: intake, compression, combustion, exhaust. Intake: the intake valve opens, letting in air and moving the piston down. Combustion stroke: the piston reaches the top, fuel is injected at just the right moment. Combustion stroke: the fuel is ignited, forcing the piston back down. Exhaust stroke: the piston moves back to the top, pushing out the exhaust created from the combustion out of the exhaust valve. Diesel engines use direct fuel injection. The diesel fuel is injected directly into the cylinder. The injector on a diesel engine is its most complex component, and it may be located in a variety of places. The injector has to be able to withstand the temperature and pressure inside the cylinder, and still deliver the fuel in a fine mist. A diesel fuel injector, that is controlled by a solenoid. Diesel mist distribution in the cylinder impacts performance and emissions. Various methods are employed to achieve the required injection, including in special induction valves, pre-combustion chambers, or other devices to swirl the air in the combustion chamber. Diesel engines may contain a glow plug. When a diesel engine is cold, the compression process may not raise the air to a high enough temperature to ignite the fuel. The glow plug is an electrically heated wire that heats the chamber and raises the temperature when the engine is cold, so that the engine can start. ECM, engine control and monitoring, is the computer system that manages a modern diesel engine. All functions in a modern engine are controlled by the computer systems communicating with an elaborate set of sensors measuring everything from engine coolant and oil temperatures and engine position. Glow plugs are rarely used today on larger engines. Smaller engines, and engines that do not have such advanced computer control, still use glow plugs to solve the cold starting problem. Fuel system. Fuel system principles. The fuel system is a highly specialized set of components, which must deliver the correct amount of fuel to the cylinder at the precise moment it is needed. A well-designed fuel system enables the engine to produce maximum power at maximum efficiency, with a minimum of exhaust emissions. Diesel engine fuel systems consists of the following key components: injectors, pumps, filters, tanks, and control systems. Injection systems and configurations include direct pumped, common rail, mechanical plunger, electronic plunger, all use differing pumping pressures and injector method to deliver the set fuel requirements. Fuel pumps are generally driven by the engine itself and deliver the high pressure fuel to the injectors directly, or a lower pressure to the injector plungers, which raise the pressure locally. Fuel filter principles. Filtering of diesel fuel systems to a high standard is vital. The very high pressures and precise injection equipment will be damaged or become blocked if any sediment is allowed into the system. Contamination is a major concern with any fuel system. Diesel standby equipment is very susceptible if fuel is not circulated or used for long periods. Fuel tank principles. A fuel tank must allow or provide safe, secure, and clean fuel to feed the engine. The tank must contain a given quantity, avoid leakage and limit evaporative emissions. Fuel tanks must be filled in a secure way, without sparks, provide a method for determining level of fuel in tank, venting, anticipate potentials for and protect against damage. Air system. Air intake systems can be simple, or complicated. Intake and filtering. Intake silencer, turbocharger, intercooler, and exhaust gas recirculation, and a mass airflow reader. Air intake must be carefully engineered and tuned to provide the greatest efficiency and power. The cleanliness of the air is as important as the fuel and must be filtered. Air intake silencers reduce the noise produced by the air intake, caused by the airflow changing direction and encountering pressure drops and flow changes across filters and equipment. Silencers are typically used on large or internal diesel engine. The turbocharger forces air into the combustion chamber, greatly increasing power and efficiency. Exhaust gases exiting the engine drive the turbo. An amount of additional power is consumed during the exhaust stage due to the flow restriction. Air leaving the turbocharger has been heated during the compression. Passing over a fin cooler causes temperature and pressure losses. However, The resulting efficiency increases of cooler air outweigh the loss. Passing over a thin cooler causes temperature and pressure losses, however the resulting efficiency increases of cooler air outweigh the loss. Exhaust gas recirculation, EGR, is a nitrogen oxide, NOx, emissions reduction technique. An amount of exhaust gas recirculates to the engine cylinders, replacing excess oxygen. NOx forms primarily when a mixture of nitrogen and oxygen is subjected to high temperature. The lower combustion chamber temperatures caused by EGR reduces the amount of NOx the combustion generates. Most modern engines now require exhaust gas recirculation to meet emission standards. An amount of exhaust gas recirculates to the engine cylinders, replacing excess oxygen. NOx forms primarily when a mixture of nitrogen and oxygen is subjected to high temperature. The lower combustion chamber temperatures caused by EGR reduces the amount of NOx that the combustion generates. Mass airflow, MAF, sensors are typically used when EGR is used, as it provides an airflow measurement to the control system, which is needed to offset EGR flows. Large engines have instrumentation systems rather than a MAF sensor. Exhaust system. The exhaust system is designed to move spent waste gas away from the engine. The exhaust will flow through one or more of these devices. Engine exhaust manifold. Turbocharger. A catalytic converter to reduce air pollution. A muffler or silencer to reduce noise. The most commonly used catalytic converter is diesel oxidation catalyst, DOC. This catalyst uses O2, oxygen, in the exhaust gas stream to convert CO, carbon monoxide, to CO2, carbon dioxide, HC, hydrocarbons, to H2O, water, and CO2. Diesel exhaust contains relatively high levels of particulate matter, soot, consisting in large part of elemental carbon. Diesel oxidation catalyst, DOC, and particulate filters are commonly as one unit. Large industry engines may have industrial-size exhaust treatment processes, with wet scrubbers and chemical treatments. Cooling system. If not properly cooled, the temperature of a heavy-duty diesel engine can reach up to 2000 degrees Celsius, which would easily be enough to melt the engine. The heat must be dissipated, or the engine cannot operate at its maximum potential. Smaller engines, typically vehicles, and portable equipment will use a radiator cooling system. Coolant flows around the engine block, absorbing heat, which is dissipated over radiator fins. Coolant is pumped around the engine, into the fan-assisted radiator, and may also be recovered for other uses such as a cab heating source. A thermostatic valve, on smaller engines, opens when hot to allow flow into the radiator. Its purpose is to allow the engine to reach its normal operating temperature, and to maintain that temperature during normal operations. Larger engines may use heat exchanger configurations, with a site cooling water system exchange medium. EGR coolers are used to cool the hot exhaust gases before they return into the engine. The coolant will usually be oil, which circulated into a oil-filled radiator. Lubrication system. Motor oil or engine oil is an oil used for lubrication of various internal combustion engines. The main function is to lubricate moving parts. It also cleans, inhibits corrosion, improves sealing, and cools the engine by carrying heat away from moving parts. A basic lubrication system pumps oil from the engine pan, or sump. The pump is driven by the engine's crankshaft, oil sprays onto components, and runs back to the sump. Oil filters remove contamination to provide clean oil from the pump into the engine. Small metal fragments produced by engine wear can seriously damage components. The oil pump in an engine circulates oil under pressure to the rotating bearings, the sliding pistons, and the camshaft of the engine. Oil pumps circulate the oil to all vital areas. Lubrication of the piston and cylinder serves to lubricate the movement, ensure a tight piston ring seal, and to clean contaminants created by combustion, specifically acids which cause corrosion. Oil systems are specific to each engine type and manufacturer, and use various component combinations ensuring injection, spray, splash, or submersion occur at the required location in the required volumes. Large industrial static diesel engines may use separate oil skids, containing sets of pumps, filters, sample points, coolers, and standby systems. Startup system. It takes extra effort to start a diesel engine when it is cold. Heat generated during a cold start is first absorbed by the engine block and surrounding components, resulting in temperatures below that which is necessary for combustion. Most diesels use batteries and starter motors to turn the engine until combustion starts. The electric motor engages during the ignition operations. Large engines are not able to be turned over using starter motors because of the high compression ratio and size of the equipment. Compressed air is used as a starting medium on very large equipment. Compressed air forces the piston from the just past top dead center position down the barrel and switches to the next piston in turn until the engine is cycling and starts. Compressed air is also used at startup to blow over the cylinders to ensure no water has built up. Water does not compress. Glow plugs have been widely used to heat the air/fuel on startup. Some modern engines now inject diesel at such high pressure, it generates its own heat for startup combustion. Many engines use resistive heaters in the intake manifold to warm the inlet air for starting. Starting agents can also be used, such as ether introduction into the inlet manifold. Heaters are also used to warm the entire engine block, on some engines especially if on emergency standby duty. Speed control system. Diesel engines, unlike gasoline engines, are not self-speed limiting, because the air, oxygen, entering the engine, is always the maximum amount. A mechanical governor regulates the idling speed and maximum speed of the engine by controlling the rate of fuel delivery. A governor is a mechanical device in the injection pump on older diesels. The accelerator pedal does not control the amount of fuel into the engine, it commands the engine to run at a certain speed. The governor controls the position of the fuel rack in the pump to control the volume of fuel injected in each cylinder. The governor controls the fixed engine speed by automatically adjusting fuel pump settings, while the power output changes to meet demand. Newer diesels govern the same thing in software. The crankshaft is connected to a position sensor, the injectors are computer controlled. Vehicle speed limiters are also in the same software. Mechanical governor assembly. Diesel engine runaway is a rare condition affecting diesel engines, where the engine goes out of control, consuming its own lubrication. Diesel engine types, basic designs. Diesel engines are generally used for power generation and backup standby, remote locations applications, fire pumps, and vehicles within the oil, gas and petrochemical industry. Engine cylinder configuration is based on power requirement and size restrictions. Inline, the cylinders are arranged in a line in a single bank. V, the cylinders are arranged in two bank sets at an angle to one another. Flat, also known as horizontally opposed or a boxer, the cylinders are arranged in two banks on opposite sides of the engine. The ability to deliver the correct power to a balanced drive shaft is the critical requirement. Engine key components, component descriptions. Cross-section of a diesel internal combustion engine equipped with a pre-combustion chamber. The crankshaft turns this linear motion into a rotating motion that provides power to move a vehicle forward, operate generators, or otherwise give measurable activity. Diesel engine crankshafts are heavy-duty yet precise, and subject to extreme stresses, generally forged steel, with various finishes, polished, or chromed. Cracks, where marks, bends, and shears are caused by excessive heat, bearing failures, and incorrect balances in firing. The connecting rod or conrod connects the piston to the crankshaft. Together with the crankshaft, they form a simple mechanism that converts linear motion into rotating motion. The connecting rods are made from steel, but may be made from cast iron, or lightweight high-strength materials such as tungsten. Connecting rods are under tremendous stress, stretching and being compressed with every stroke. Metal fatigue, heat stress, lubrication and bearing failures are common failure modes. Pistons transfer force from expanding gases in the cylinder to the crankshaft via the piston rod. They also compress cylinder gases on the upstroke. Pistons can act as valves covering and uncovering ports in the cylinder wall of a two-stroke diesel. The majority of damaged pistons are due to the air/fuel ratio, or fuel injection alignment causing overheating, or erosion. Scuffing can cause seizures of the piston in the cylinder. A piston ring is a split ring that fits into a groove on the outer diameter of a piston, seals the combustion chamber, transfers heat from the piston to the cylinder wall, regulates oil lubrication consumption. Piston rings can be in many different configurations. The most common configuration is a top, bottom, and oil 3-ring combination. Piston ring failures are commonly caused by the lack of lubrication or contamination. Oil contaminates broken rings, allow pressure leaks, score cylinders, and can cause catastrophic failure. The cylinder is the space in which a piston travels. Multiple cylinders are arranged side by side in an engine block, typically cast from aluminum or cast iron before receiving precision machine work. Cylinders may be sleeved, lined with a harder metal, or sleeveless, with a wear-resistant coating such as Nic Hazel. Cylinder common failure: failed lubrication can cause the pistons, or piston rings, to seize to the cylinder wall. Seizing can occur during engine use, via overheating, and lack of oil, or during storage, via condensation and corrosion. The cylinder head sits above the cylinders on top of the cylinder block. It closes in the top of the cylinder, forming the combustion chamber. The joint is sealed by a head gasket. The cylinder head provides passages that feed air, fuel, and allow the exhaust gases to escape. Valves, timing gear, fuel injectors, and camshafts are commonly mounted onto the cylinder head. Cylinder head common failure: cylinder heads can crack, leading to catastrophic failure. Common faults are gasket failure, leading to compression loss, and erosion. Skimming grinds a smooth level surface in damaged heads. The camshaft runs the length of the cylinder bank, with a number of oblong lobes protruding from it, one for each valve. The lobes force the valves open by pressing on the valve, or on some intermediate mechanism as they rotate. The relationship between the rotation of the camshaft and the rotation of the crankshaft is of critical importance. The camshaft is connected to the crankshaft either directly or via a gear mechanism. Camshafts tend to be damaged following the failure of other components, such as the lubrication, valve, or timing systems. Over long periods, lobes can become pitted, which can lead to cracks and failures. Controlling the timing of fuel injection is key to minimizing the emissions and maximizing the fuel efficiency. Fuel injection timing is carried out in modern engines by the ECM, engine control and monitoring. The ECM uses sensors to inject the correct pressure of fuel at the correct time. Injections are set at specific times based on the engine requirements. The mechanical timing of the valves is controlled directly by the crankshaft to the camshaft by a timing chain or belt. Belt and chain tension faults, usually snapping or breaking, are the common mechanical timing failures. ECM component malfunctions account for the electronic timing failures. The diesel pump is the device that pumps fuel into the cylinders, driven indirectly from the crankshaft. Fuel is injected only very slightly before top dead center of that cylinder's compression stroke. The common fuel pump failures are normally caused by general wear, fuel contamination wear, and electrical/electronic failures. Low pressure feed pumps to the high pressure unit are typically less robust. Diesel engine applications. A diesel engine and fire water pump combination. This is a mobile, portable, diesel engine and fire water pump combination. A diesel engine driving an electric generator. An external diesel engine providing power or backup emergency power. Multiple engines used for electrical power generation. Small electrical power generators. A mobile electrical generator, typically used during a supply outage. Very small mobile equipment power generators are used for low power field activities. A mobile diesel powered air compressor, used to drive air-powered equipment. A diesel-powered welding plant. A diesel-powered high-pressure water jetting unit. The majority of large construction equipment uses diesel power to generate movement directly, or drive motors and pumps. Pre-startup checks, common pre-startup checks. Diesel engines are produced by many manufacturers in a multitude of sizes and component configurations. They all require a pre-startup check. The general pre-startup requirement is to ensure the following key areas: no damage or missing components, oil system levels are correct, coolant levels are correct, fuel system levels are correct, valves and drains are correctly set, components such as belts are correctly in place. The pre-startup check is primarily visual. Extent of the checks depends on the engine, its size, and the duration of time since its last use. Serious damage can occur if an engine is run without air filters, oil, or water in the cylinders. The importance of the visual inspection and understanding your equipment is vital for a successful startup. Each engine will have an operating manual from the manufacturer. This is considered a key engine component. The pre-startup check must be completed as recommended. Warranties require use of the manufacturer recommendations. Never attempt to start up a plant or equipment, including a diesel engine, unless you are trained and authorized. Routine checks during operation. Common checks. The routine operational checks on a diesel engine, as with the pre-startup checks, are various and depend on the manufacturer and size. Common routine checks, oil level checks, are carried out on a very regular basis. Oil samples are taken to check quality and examine trends. Visual checks of the air intake system and indicators, if fitted. The air filter should never be removed and checked when running. Cooling fluid checks are carried out using local gauges or control panel mounted indication. Cooler performance may be indicated using differential temperature. Coolant fluid level checks. Coolant temperatures may be logged in the ECM. Checks may be physical levels or generated sensor readings. The operator will listen for changes in engine noise during checks. Vibration monitoring may be used. The operator may detect variances during routine checks, with support from instrumentation. Fuel supply tank level checks must be carried out. Fuel filters may have a water drain. To clear contamination, fuel supply and filtering is critical. Running a system dry of fuel can cause restart problems with airlocks. Visual checks can assist in positive confirmation of flow and level. Cooling water flow can be confirmed with visual flow indicators. Oil level gauges can be used to indicate level. Visual checks can indicate possible problems. Gas emission monitoring and soot analysis can also detect problems. Visual indication of serious problems can often be seen in the exhaust flow. Detailed monitoring can identify early problem development. Modern engines have complex systems and monitoring sensors. Data logging and trending greatly increases monitoring capability. Manufacturer operational instructions must always be used to develop a monitoring basis. Routine checks form a vital part of any condition monitoring, and with maintenance, will extend the life and usability of the engine. Troubleshooting common diesel engine problems. Troubleshooting is a form of logical systematic problem solving. The following set of common problems are accompanied by generic troubleshooting examples. Specific engine detailed troubleshooting will be part of the operating manual and must be used. Engine does not turn when starter is engaged. Possible cause: battery connections loose, broken, or corroded, creating excessive resistance. Battery is not properly charged or has failed. Possible solution: check the battery cables and connections, ensure that connections are clean and tight, recharge the battery. If the battery does not take the charge, replace it. Possible cause: engine computer system, ECU, or wiring faulty. Possible solution: check all plug connections. Possible cause: engine running, gear blocked, engine will not bar over manually. Possible solution: possible serious engine damage, seizure, consult an engineer. Possible cause: starter motor or wiring is malfunctioning. Possible solution: replace the starter motor or repair wiring. Exhaust smoke common fault finding. Black smoke, blocked air filter, faulty injectors, or engine overload. Blue smoke, excessive engine oil, oil separator crankcase breather clogged, or a faulty exhaust turbocharge, cylinder head, piston rings, or cylinder line. White smoke, engine temperature low, water in the fuel system, or intercooler leak. Troubleshooting can be very simple, for example, high temperatures caused by low oil level. Or very complicated, for example, computer control sensor faults, or problems that are inherent in the engine such as knocking. Safety considerations, diesel engine safety. A diesel engine should be considered the same as any other process plant, or equipment, high temperature, noise, toxic gases, flammable liquids, stored energy, and electricity. Noise levels around diesel engines can be very high, and ear protection should be worn. Hot surfaces, such as the exhaust system, should be guarded. Oil and diesel contact with the skin can cause health problems such as dermatitis, and must be avoided. Housekeeping and spill cleanup is important to avoid slips on oil or diesel, especially when carrying out at elevated work. High-pressure fuel systems and retained pressures can inject fuel through the skin into the body. Always ensure the system is fully depressurized before starting work. In 2012, the World Health Organization reclassified diesel fumes from probably to definitely causes cancer. To avoid fume inhalation, always ensure adequate ventilation or extraction. The use of PPE should be based on the task assessment and will generally include gloves, hearing protection, safety glasses, and hard hat, and possibly thermal protection, overalls. Engine air intake shutdown, shut off, valves, prevents overspeed of the engine, if any flammable gases are drawn into the intake. Module end. You have come to the end of the diesel engine training module. Take time to review the module, and seek assistance if you require further information. This module supports your procedures, and the engine manufacturer's user instructions, which should be read and understood.